Okay, finally we come to the neural networks themselves. They come under many names. So we're talking the multilayer perceptron, also known as feed-forward neural network, also known as an artificial neural network. Actually, when you say artificial, you don't specify what type exactly, but the most frequently used type by far are these feed-forward neural networks. So these networks combine several perceptrons to create a nonlinear decision boundary. And that works as follows. Coming back to the handouts, the basic trick is that each perceptron gives a nonlinear mapping to a new dimension, and perhaps in this new dimension the problem is already linearly separable, or else you can iterate this process. So iterate from these new dimensions to yet another new set of dimensions and so on until in the end they become linearly separable. So let's look at the example here. Clearly the blue and the red class are not linearly separable. However, if I now use two perceptrons, I can ask, does my sample of interest lie above, and by above I mean pointing in the direction of the normal vector, does my sample lie above the first perceptron, and does my sample lie above, again indicated by the normal vector, above the second perceptron? If both answers are true, then I'm going to predict the blue class. So what I need is a minimum of 3 perceptrons, perceptron 1, perceptron 2, and then in words I said and. Does it lie above the first and does it lie above the second? And this and operation can also be embodied in a perceptron. And on the right hand side, by the way, you see a picture, and indeed this is the first perceptron. This is should be a summation sign. This is the second perceptron, and that is the third perceptron, the one which does the AND operation for you. Now, it is important that these mappings by the perceptrons in the first layer of neurons, that they should submit their output to a nonlinear activation function. And in the bottom row, you see what happens for a variety of so-called activation functions. And by the way, these activation functions here are symbolized by the sigmoids in those boxes here. So if you use a linear activation function, then you merely use an affine projection of your data. So this is, let's say, this is the output of the first perceptron. I'm going to call this output S1 and S2, and these are my axes S1 and S2. And if I use a more or less linear activation function, then I obtain something which is a rotated or rescaled version of the original data set. So nothing very interesting has happened. This has not helped my separability. If, on the other hand, I make these activation functions very crisp, so here, in fact, I used a step function. So the output of a perceptron was either +1 or -1. You then see that I now get a very different picture here. So all points in, let me understand what I'm plotting here. Okay, I'm confused about not seeing a red dot down here. But it's not a fake. I mean, I computed this, you know, with a script. It's not. I didn't hand plot this figure. I have to look at it. So what I asked was to have each perceptron say, do the okay. I think I might have changed around the classes. Could that be? Not really, huh? Okay, I can't figure it out yet. So what I asked was, for each perceptron, I asked, does a sample of interest lie above the first and above the second perceptron? And in case of the blue class, I got an affirmative in each case. So all the blue points end up here. They get a +1, +1. Now, these red points here, they are above one perceptron and below the other, so I get a +1 and a -1, whereas those are below the one perceptron and above the other. They end up here. And the thing I'm confused about is I would have expected these points that lie below both perceptrons, I would have expected them to lie at -1, -1, and I don't see anything here. So I have to look up what I computed. However, you see that now in this artificial space that is no longer, so these were the original dimensions, x1 and x2. And now I have these artificial dimensions, s1 and s2. And in these artificial dimensions, the problem now does become linearly separable. So I have the blue class and the red class, and I can now find a perceptron in this new space which will separate the two classes. And now in between, I have used more or less extreme activation functions. So here, the activation function was just the identity function. It did nothing. Here, the activation function was a step function. And in those cases, the activation function was something that was relatively sharp. Sorry, this should go through the origin. And here, relatively smooth, but still sigmoidal. And what I wanted to show is that using such using some kind of nonlinearity in the activation function is really, really important, because otherwise, if you use a linear activation function, you just map your data to a different space, but it doesn't change the geometry of your data sets. Whereas with a nonlinear activation function, you get a nonlinear mapping, and in such a space, you may be able to linearly separate your data. Yes? No, activation function is not the same as the loss function, but it's a good question. So let's look at that in more detail. I used this funny graphical notation now. I will start with the notation for a single perceptron. So we have a couple of inputs, x1 and so on up to xp. And now if I use this homogeneous representation, I will have an extra input which is always 1. And these inputs, well, this summation here, it really symbolizes the inner product between my inputs and my parameters. So this is W1 tilde, WP tilde, and down here my bias. So this thing here is just a complicated way of writing the inner product X transpose W. And this output is now piped through the activation function, which is typically a sigmoidal, so that at this point I now have, and this is why I used an S before, this should be reminiscent of sigmoidal. So at this point here I have my sigmoidal function evaluated at coordinates or at position X transpose W. And you see that these were my original inputs, and down here I have now produced a new artificial input. And if I call this whole thing perceptron 1, then perhaps let me write here S1 of X transpose, and then I should also give a subscript to the vector. W is now an entire vector, and the 1 is not an element of the vector. It just says that this is the parameter vector of perceptron 1. And now I can replicate this entire structure. So in particular here, you see that I have now combined, I now have 2 perceptrons in the first layer, and they produce these artificial new dimensions, and then I have a perceptron in the second, or in the output layer. And in this case here, the single layer or the single perceptron in the last layer would perform the linear discrimination. And your question had been if the activation function is the same as the loss function, and that is not so. So activation functions that people use are, for example, the logistic sigmoid or the hyperbolic tangent. And loss functions that people use, they will depend on what you're trying to predict. So if you do regression, logistic sigmoid is the first thing I wrote, and hyperbolic tangent, tangens hyperbolicus, is the second thing that I wrote. If people do regression, you can even use the normal squared loss as the loss function, or if you do classification, you can use the cross entropy error function, for example, and so on. And one should not mix and match these wildly. One should rather match them. So let me try and reproduce the cross entropy error function. I assume that my true labels in this case are either 0 or 1, and I assume that my predictions are from the interval 0 to 1, and it is derived from the log likelihood. So we have a product over all samples, and then we have, I need to figure this out, I think we have yi hat to the power of yi. Don't copy this down yet, I need to make sure this is correct. So if the true label is 1, then I want my prediction to be as large as possible. And if the true label is 1, then this whole thing here will contribute nothing. It won't change my product. This will just multiply with 1. Whereas if the true label is 0, then I want this expression to be as large as possible, which seems to be right. And if I now take, sorry, this was the likelihood, not the log likelihood. And if I now take the negative log likelihood, then I end up with minus sum over I yi times ln yi hat. Yeah, sorry. At least you don't see any errors I'm making. Okay, I hope this is correct. If so, then this is the cross entropy error function. And the y hats are, of course, functions of the parameters that you used. So I just omitted the w everywhere. And in that sense, this is also a function of your parameters. And this cross entropy error function, the likelihood that I showed here was the likelihood of a binomial of a logistic regression. And that would, for example, be logically and numerically the right match if you use as activation function the logistic sigmoid. So conceptually it would be the right match because you use two pieces of mathematics that have been motivated with the same arguments on the one hand, and numerically it means that you obtain relatively nice expression for the gradients in your backpropagation procedure. So we have, but the question was, are activation function and loss function the same? And no, they are not. And typical loss functions include the squared residuals for regression, or this cross entropy error. But people are using others. And even here, people are using other activation functions also. Okay. Now, we have looked at a single example, but if you generalize the idea behind this example, you come to what is known as the projection trick. Go ahead.
In the examples, you have like C, D, and in example C, you said that the activation function was the identity, but then still like the plot was somewhat different. So
because the normal vector, so the question is, we have here, I claimed an identity activation function. Why then does this data set look different from that? And the reason is that the normal vectors are not aligned with the axis of my original feature space. So I can now try and figure out which perceptron was which. But you see, essentially, if I use the logic that I've just used, I have to, for the first axis, rotate my first perceptron such that its normal vector, let's say, points upwards. And then the y position will give me the first coordinate, and similarly for the second. But it's not just a rotation, because nobody requires that these be at an orthogonal angle. And in fact, they are not. So these two perceptrons are not quite orthogonal. They can be at any oblique angle. And then this will give you an affine distorted image of the original data. But if you look at the formula or at these diagrams, you will see that you could have represented the action of that set of perceptrons merely by a matrix multiplication. So you see, this summation is linear. So this is the inner product. If we now put it through the identity function, this is like the action of a single row of a transforming matrix. So it is this nonlinearity that really makes neural networks what they are. It is crucial to have this nonlinearity. And this is why we get a qualitative difference here between the first plot and then the later ones. More questions? Okay. So the question is how to make sure that we don't get two identical perceptrons. That it could happen, but it shouldn't. So we haven't talked yet about how this thing is trained. Really, it is trained by, for example, initializing all parameters randomly and then doing a gradient descent of this entire structure. And I've never seen it happen that two perceptrons end up, identically. So if you look at it in terms of a matrix, you would say that it becomes rank deficient. You could detect it, and then so if two perceptrons become virtually identical, you could detect it and then reinitialize one of them. But I don't think it's a problem in practice. In this case, yes. In this case, I have nicely arranged my perceptrons so that they exactly do what I want them to do. And so, yes, I've not talked about training here. I've just talked about how to, given that it's trained already, how would you do prediction on any new point? Well, if you want to talk about training now, it's a fair question. We can talk about it now rather than later. So whole books have been written about it, but there's not so much to say, really, I think. Omitting all the fine details. So training is by backpropagation. And let's look at this diagram here again. And let's call this thing here S3. So the final output that I get, so my y I hat of all parameters w is a nonlinear activation function S3 of, and now I need to, notation will become a little bit messy. So I'm now using a so let's say the first subscript is the index of the perceptron, and the second index would be the coefficient of the vector that I'm looking at. So W3 would be all the parameters of the third perceptron, and now I'm multiplying the first coefficient of this vector with the output of the first perceptron, which I'm here abbreviating as just S1, plus W3, 2 times the output of the second perceptron, S2, plus I also have a bias. So that's the output, and now I can iterate this. So now I can say, by replacing S1 and S2, I can say this is S3 of W3, 1 times S1 of X transpose times W1. Those were the parameters of the first perceptron, plus W3, 2 times S2 of X transpose W2 . So what we have here is a nested expression. And I could write, now what I've written here was specifically for this multilayer perceptron that you saw here, but I could write it in a more abstract fashion by replacing every addition by a summation and so on, which will make an even worse mess of my indices. And the thing is, we now want to compute the derivative of this thing with respect to the parameters. I did that on purpose. So I get some criticism for my notation here. It would have become even longer. So to write it out explicitly, times S1, because here I abbreviated by writing X transpose. So I would have had to write this as X1 times W11 plus X2 times W12 plus analogously there. So I don't see the problem yet. Okay. Two comma 1 plus X2 times W2 comma. It's the index of the perceptron itself, the first index. I didn't use the layer number. I just numbered the perceptrons 1, 2, 3. Which isn't great, I agree. Okay, plus W3, 3. But the point is, we have a nested expression. So if forgetting about all details, it looks roughly as follows. I have a function A of a function B of a function C of, you get the idea. But let's say it already ends here. And if I'm now interested in the derivative of this thing, with respect to W, you have to remember these differentiation rules. So this is A prime of B of C of W times, well, the derivative of B of C of W with respect to W, and so on. So you can unnest these expressions one by one, and this is really what you do for backpropagation. What is this rule called? It's not a rhetorical question, I always forget. Chain rule, thanks. Yeah, so it's so backpropagation, to my mind, is iterated application of the chain rule. Now, why books are written about it and why it's worth actually writing them is because it turns out that if you match the activation functions and your loss function properly, then you get out very simple expressions for these derivatives, and you then get expressions that look like messages that you pass up your network. So the input, the network takes input which is passed from beginning to end and produces output. And in the backpropagation, this is where the name backpropagation comes from. You take the residual of your output, which you would like to reduce, and you from that deduce messages that walk from the end of the network to the beginning. And so you propagate backwards this information of how wrong your prediction was and how you should modify the parameters in the network to get it right. Now again, I've only shown this for this concrete example of this particular tiny network here, and you can do that more nicely by having indices that really refer to the layer and to the number of a perceptron within a layer and so on. But it's a lot of notation, and it doesn't change, to my mind, the ultimate message or understanding. Okay, so you would randomly initialize with some set W, and you would then compute the loss and then compute the derivative of the loss with respect to your parameters to find out in which direction you have to change them in order to get a better prediction to minimize your empirical loss. And it works, except that you will typically end up in a local optimum. Is that okay? Yes? No? Maybe? Can you ask more questions? Why did I write that? Or above? Why is it equal? Why is that an equality here? This was an abbreviation. I just wanted to say this last perceptron here takes as input the output of the first perceptron. So this thing here is perceptron 1, and that thing here is perceptron 2, and this is perceptron 3. And you see the original perceptrons had as input the original features, and the second layer perceptron has as input these artificial features that were generated as output from the first perceptrons. And I abbreviate the output of the first perceptron by S1, and I abbreviate the output of the second perceptron by S2. So up here, I could, in this expression here, I could no longer write X transpose W, but I would have to write something like S transpose W. And this S1 was a shortcut for what an abbreviation for what I've written in more detail down here. They are not the same. So this is the last thing here that's not an identity, except that, I could say that this summation here is also a function. So I could say that this is function A, and then the fact of having the summation here would be function B, and then that there the analogy stops, because here I have a function C and there I have a function D, but it's nested in that sense. Yeah? Exactly. I want to minimize with respect to all parameters W. Exactly. Now those questions are very good because they help clarify the matter. More questions?
So basically, I'm just looking for the
You're looking for the position of all your individual perceptrons, which is given by slope and intercept, or in our parameterization by normal vector and distance from the origin. Yeah, so yeah. It's so here that was a single prediction y hat, and now I have a loss function which looks, so my loss function, it's a function of all the parameters W, and that's summation over all samples. And now I'm just writing an L to say this is any loss function, and then in this loss function enter the true observation or the true label. It could be a class for classification or a value for regression. And in this loss function enters my current prediction, yi hat, which is a function of the parameters. And in the last hour, we have discussed various loss functions. We've looked at the 0-1 loss or at the hinge loss, and there are other possibilities. And the loss function, this is the empirical loss. If you sum it up over all observations, it gives you this error as a function of your parameters W, always for a given training set. I've omitted here the reference to the training set because it's always the same training set I'm talking about here. And now we take the derivative of this quantity with respect to all the parameters. And down here I only sketched the derivative of a given prediction with respect to the parameters, because the prediction, it somehow appears in the loss function. So eventually when I compute this derivative, I will get to this point of computing the derivative of my current prediction with respect to the parameters. But really it is this thing here, the empirical loss. This is the empirical loss. And this is really the thing that I want to minimize by backpropagation. And it is called empirical loss because this is always the loss that I compute on my training set. So this is not the real loss out in the wild, the performance I would get on a test set, but the good loss functions, they somehow mimic this behavior. So the good loss functions or a regularizer that you can add to your loss function, they try and make sure that you do not totally overfit your data. for the optimum parameter values. So coming back to this picture here. Now the picture that I had plotted here was just for a single perceptron. But, you know, more in a more abstract fashion, we here have what I've plotted here was the empirical loss. And as you now combine more perceptrons to get a neural network, your number of parameter grows. So I can no longer plot this as a two-dimensional function, but it would be, let's say, a function of 20 parameters. And you want to find, ideally, the global optimum in this parameter space. In 2 dimensions, I can just, you know, plot a picture and say the minimum is here. In 20 dimensions, you can no longer afford such a grid search, and this is why you use gradient descent. And gradient descent for neural networks, if you use the chain rule, is called backpropagation. Oh, the fault lies with me, if I don't make this clear. You have a comment? It's, yeah, unfortunately, it's not unique. It has many local minima, and that is due, well, you know, it becomes hard to plot these spaces. The best picture I showed you so far was this one here. This was still just for a single perceptron, but if you look closely, you already see that there's a local optimum here and a local optimum there, which comes in this case because I used a non-convex loss function. And this effect of having multiple local minima is exacerbated when you have many perceptrons that you combine in a nonlinear fashion. It's perhaps something you should try out in the exercises, you know, that you reinitialize multiple times and you compare the solutions and you see they're not the same. More questions? Yeah, if you, it's no contradiction. So in general, you build the derivative of this empirical loss function, and for the particular case of the hinge function, I ignore, excuse me, I ignore the correctly labeled samples, and for the incorrectly labeled samples, I do exactly what's written on this sheet here, because you know, I sum up the outputs of the last, or I sum up the outputs of the last neuron for the wrongly classified samples and multiply it with their true label. And what I wrote here was exactly the output of the last neuron for a single sample. So if I use the hinge loss function, then this is essentially it. But if you use another loss function, this is why I wrote this equation here, things can, well, you know, then you also have the loss function itself entering, or that needs to be differentiated. And the hinge loss is trivial to differentiate, and others look a bit more complicated. Okay, and I've not really finished the calculation here because, you know, I just say then you differentiate this, but I haven't done it explicitly. So it would depend on what sigmoid function exactly you use and so on.